Welcome back. We are in the next lecture in electronics. We were discussing on the controlled rectifiers. In the previous lecture, we saw on the center tap full wave rectifiers. Now we will focus on the bridge rectifiers and how it is used, what is its analysis and the performance. So first we will introduce about the single phase control rectifier, especially in the bridge configuration, and then we will see the analysis in the full wave with different type of loads such as the resistive load and the combination of resistance and inductance load. Also we will see the role of freewheeling diode in the RL load and how the performance is improved. We will also take up the load which is combination of RLE. Here E stands for the EMF, and we will see the inverter mode operation of this rectifier. So we have seen that in the single phase midpoint full converter, some of the key characteristic about the average output voltage, which is 2 Vm by pi cos alpha. Average output power can be calculated as the product of the DC voltage and the DC current, which is 2 Vm by pi cos alpha multiplied with the DC current. The peak inverse voltage, where each thyristor has to withstand twice the maximum value of the supply voltage. Now for a design case, if we take the maximum power output, we will get 7643.31 watt at the firing angle 0 when the DC current is 50 ampere. So here some of the circuit features are: it requires the center tap transformer, and there will be lower transformer utilization and higher peak inverse voltage requirement. So these limitations, whatever we have, basically lead us to move into the bridge converters. So now in the bridge converter, the peak inverse voltage, where each thyristor will has to withstand only the maximum supply voltage Vm, which is 2 Vm in the case of center tap. So additional advantage is that we don't require any center tap transformer, and hence we will have better transformer utilization. Here again the DC output voltage will be 2 Vm by pi cos alpha, and the maximum power output, if you can see, it is by double at the same condition where alpha is 0 and the DC current is 50 ampere. So we can say the advantage is same power rating we got in midpoint converter, but with lower PIV requirement, peak inverse voltage requirement. So the comparison, if we do that, bridge converter can operate at maximum voltage of 480 volt compared to the midpoint converter limitations. So compared to the midpoint converter, we find the bridge converter has twice the power rating, and the PIV is also reduced. Some industrial applications we have extensively, which is used in DC motor drives, the battery charging and electrochemical process. We have the capabilities of these which provide unidirectional current. It will provide the current in both positive and negative average voltage. 4-quadrant operation will be there, where we have the rectification mode as well as the inversion mode. The continuous current capability will be there for the inductive load. So in compare with the load, resistance and inductance, it will have a different feature. What are the limitations we have here? That we will be requiring 4 SCRs with a complex gate drive circuit. It will have higher harmonic content, and the power factor will be poor at large firing angle. The control circuitry is going to be complex. If we classify the bridge rectifier, single phase controlled bridge rectifier, it will be either half controlled or it can be full controlled. Again, half controlled rectifiers can be asymmetrical or symmetrical. So for symmetrical, we have common cathode configuration or common anode configuration. So this is what the detail we are going to discuss one by one on the bridge rectifiers. Some of the key differences in half controlled and full controlled, if we see, in half controlled we have 2 SCRs and 2 diodes. So here you will have unidirectional power flow, whereas in full controlled we will have 4 SCRs. So there is a bidirectional power flow. So whenever we require bidirectional power flow, we move to full controlled bridge rectifier. If we require only unidirectional current flow, then we can prefer half controlled rectifiers. Let us first discuss the single phase full control bridge rectifier with a particular type of load, which is the resistive load. So here we have the circuit of full wave bridge rectifier, the load is the resistive load. The input that we give is basically single phase AC supply. So the circuit features, if we see, it will be consisting of 4 thyristors now, T1 to T4. And these thyristors will be connected in the form of the bridge, and then it will be connecting with the resistive load. If we see the diagonally paired SCRs T1 to T4 will conduct alternatively. So first the conduction will be for T1 and T2, and then we will be having T3, T4 conductions. So diagonally paired SCRs will conduct together. Natural commutation will be there at zero current crossing, and the conduction angle in this case will be pi minus alpha for each pair of the thyristors. In the operating principle, if we see in the positive half cycle of the AC wave, where omega t is from 0 to pi, SCR T1 and T2 will be triggered at omega t equal to alpha, alpha being the firing angle of the thyristor. In the negative half cycle, omega t from pi to 2 pi, T3 and T4 will be triggered at omega t will be pi by pi plus alpha. So the load voltage will follow the input voltage magnitude when the SCR conduct. Since the load is resistive in nature, the current and voltage will be in phase with each other. So this is the waveform of single phase full wave controlled bridge rectifier with the resistive load. So first we are showing the input supply voltage, which is the AC single phase, and the gate signal that we give for the two thyristor combinations Ig1 and Ig2 at the conduction firing angle of alpha and pi plus alpha, and then it will repeat. So this is the output voltage and output current which we will be getting after the conduction for alpha to pi, and then again pi plus alpha to 2 pi. If we see the voltage and current, both are in phase with each other. The thyristor voltages are shown for the combination of T1, T2 and T3 and T4. Let us do the performance analysis for the resistive load. Average output voltage we will get, that is 2 root 2 V by pi cos alpha. So this is what we have, the DC voltage. DC current can be estimated by dividing the resistance to the DC voltage, and the RMS voltage can be computed using this formula, which is dependent on the firing angle alpha and the voltage B. Form factor again can be estimated by the ratio of RMS voltage by DC voltage, and the ripple factor is under root of form factor square minus 1. If the load is RL in nature, what will happen in the performance? So that is what we are going to discuss. So here the circuit behavior will be, the inductance will cause the current to lag the voltage, which is the property of the inductance, and it will cause to operate in the continuous and discontinuous conduction mode, similar to all the previous discussion that we have when the load is inductive in nature. Boundary depends on the elements L and R and also the firing angle alpha. Critical inductance will be determined for the mode transition. So we will see this in the continuous mode when the inductance value is greater than the critical value, or we have high load inertia. In the discontinuous mode, when the inductance is less than the critical value, or we say that light load condition, we will get discontinuous current operation. Time constant of this circuit will be L by R, which will influence the decay nature of the current. Let us do the conduction mode analysis for the continuous conduction mode analysis. We have the DC voltage, which is 2 root 2 by pi cos alpha V, and the DC current again can be estimated by the ratio of VDC and R. Here the RMS voltage will be V under root pi plus alpha by pi for highly inductive load, because we have the continuous nature of the current. Form factor again we can estimate from the value of RMS voltage and the DC voltage. Now let us see the waveform. So in the continuous load current mode, if we see here the voltage V0 and the current I0. So I0 being continuous in nature with no breakage, because we have the load which is highly inductive in nature for the RL load combination. In the discontinuous current mode, the DC voltage will depend upon two factors. One is basically the alpha value, and other is the beta value. So this is VDC, root 2 by V by pi cos alpha minus cos beta. The average load current again can be estimated from VDC by R, and the RMS voltage can be calculated using this formula. Here the beta being the extinction angle. So this is what we were discussing in all the previous lectures on this controlled rectifier, how the beta plays an important role in the extinction angle for the inductive load combination. So here we can determine the beta only when we substitute that the current at beta will be 0 condition. We can get what is the angle beta for this particular load combination. So here we can see the current I naught, which is discontinuous in after beta 2 pi plus alpha. So in the discontinuous load current mode for single phase full wave bridge rectifier for the RL load combination, current will not be continuous. It will be discontinuous at the extinction angle beta. Now we were discussing again in the previous few lectures the role of the freewheeling diode, which is placed in parallel with the load combination of RL. So the freewheeling diode will be connected across the load and it will conduct when the load voltage attempt to reverse. So here when we are giving the AC voltage and the AC voltage is going to reverse, then the freewheeling diode will be coming to conduction process. Here the clamp's minimum load voltage will be there to 0, and it will prevent the inverter mode operation where the DC voltage is greater than equal to 0 always. So some of the advantages of these freewheeling diode, it will reduce the current ripple significantly, and it will improve the load current. It will provide the better transformer utilization factor, and it will reduce the harmonic distortion which is there in the load current and enhance the system reliability. So if we do the performance analysis for the average output voltage alpha lying between 0 to pi by 2, we will have the VDC, which is root 2 V by pi 1 plus cos alpha, and the average output voltage, and from pi by 2 to pi we will be getting the DC voltage to be 0 because the freewheeling diode conduct continuously here. Input displacement factor will be cos alpha, and the power factor improvement will be possible because we will have better power factor, which is not possible when the freewheeling diode is not there. So this is the waveform of the voltage and the current in the continuous and the discontinuous mode. So we can see here the current which is continuous, and here the current is discontinuous. So here we have the freewheeling diode which will be improving the power factor now, and also the harmonic distortion will be reduced. The next load combination that we take is basically the RLE load. So here we have resistance, inductance, and the EMF load combination that we have. This primary application generally is seen in the DC motor speed control. So in the DC motor speed control, we will have the RLE load combination where R stands for armature resistance, L stands for armature inductance, and E stands for back EMF. The circuit equation, if we write, then we will have root 2 V sin omega t, which is the input voltage, and the voltages across the inductor and the voltage of the resistor and the source of the EMF E can be equated in accordance with the KVL equation. So root 2 V sin omega t is the supply voltage during the conduction period here. What is the operating conditions we have? The SCR will conduct only when the supply voltage is greater than the motor back EMF, and the minimum firing angle that we get is from the equation sine inverse of E by root 2 V. And alpha, when it is less than the minimum value, then there is no conduction possible. Now, if we do the discontinuous analysis, current analysis, so the expression of the current for value of the omega t lying between alpha to beta, we have this expression. So here we have the transient and the steady state with the load impedance and the load phase angle given. Average output voltage and the current can be estimated using these formulas, and the boundary condition we can give where the current at beta is 0, so we can estimate what is the beta value that we have. So the voltage again will be dependent on alpha and beta both, beta being the extinction angle. So for the RLE load combination, this is the voltage and the current waveform during the discontinuous mode operation. So here the current is discontinuous in nature, and all the other voltages and the gate currents are basically shown. If we have the continuous current analysis, then there will be steady state operation. When the periodic boundary condition, we can have the current at alpha will be equal to current at pi plus alpha. Average output voltage we will get to 2 root 2 V by pi cos alpha, and the current we will get as VDC minus E by R. This is the current expression that we have. So in the current expression, we can see there is K, which is determined from the periodic boundary condition. Other factor phi being the phase angle of the load. Motor operation, we have the motoring mode when the DC voltage is greater than the back EMF value, and the power will be delivered to the load or the motor. Regenerative braking mode will be there when the DC voltage is less than the motor back EMF. So here the power will be returned to the supply, and the speed control is possible only when by changing the firing angle adjustment, which is possible that we can control the speed of the DC motor. So this is the voltage and current waveform for the continuous mode of operation for the RLE load. So the current being the continuous here, there is no break from pi to pi plus alpha. We will have the continuous current conduction mode possible for the RLE load combination. So the boundary between the continuous and the discontinuous conduction boundary condition is transition will occur when the current just touches the zero, and it will depend on the parameters of the circuit, that is the resistance, inductance and EMF and the firing angle alpha. It is very critical because inductance concept will be applying here, and the inductance variation will change the circuit features. So the design consideration is higher inductance favor continuous conduction. Lower back EMF will increase the conduction angle. Firing angle will affect the boundary significantly, and load characteristic will determine the operating mode, whether it is operating as motoring mode or regenerative mode. So the load characteristic will determine that. So here we can see the boundary between the continuous and the discontinuous conduction mode for different values of the parameters. So here we have the voltages V0 and the current I0, and we have the gate current, gate firing as usual, and we have the thyristor voltages appearing across the thyristors. Now we have the 4-quadrant operation. What is 4-quadrant operation? Let us discuss that. So from alpha 0 to 90 degree, we have rectification mode. So in the rectification mode, you will be converting the power from AC to DC, and the DC voltage will be greater than 0. We will get positive average output voltage. Power will also be positive, and we will have forward motoring operation in the rectification mode. Alpha being 90 to 180 degree, we have our inversion mode where the DC voltage is less than 0 and it is negative average voltage, what we say. So the power is flow is from DC to AC. Here the power will be less than 0 and there will be regenerative braking operation in the inversion mode. So the key design that we have is that the firing angle alpha, which control both the magnitude and the polarity of the average output voltage, and it will enable the seamless transition between the motoring and the regenerative mode. So when the load is RLE in nature, simply by changing the firing angle for different value, we can have the rectification or we can have the inversion possible. So here we can see the voltage and current waveform in the inverter mode operation with continuous conduction. So current is continuous here, and if we see the output voltage V0, which is in the inversion mode, we will have the negative value of the power, which is possible with respect to the V0 and I0. So what is the input current harmonics? We have to do the Fourier series analysis. When there is a continuous conduction with highly inductive load, then the source current will have certain harmonics which can be estimated using this formula, where the harmonics are basically in the fundamental frequency. This is omega, and then we have 5 omega, 6, 7 omega, 11 omega, and so on. So input current always will contain the odd harmonics. Fundamental component we can see here, which is 4 DC by pi, and the fifth harmonics and seventh harmonics we can calculate using the formula 4 IDC by 5 pi or 4 IDC by 7 pi. So odd harmonics will be present in the input. Now this is the voltage and current waveform for the bridge rectifier at high inductive load. So when the load is highly in nature, we can see that we will get the continuous I naught, which is becoming constant. We will get the constant I naught for the load. Now if we do the power quality matrix, total harmonic distortion which we need to estimate, which is the under root of RMS by the fundamental component square minus 1, which comes to be 48.34% for this particular case. So the displacement factor is cos alpha and the current distortion factor can be estimated same I1 fundamental component by RMS current, which is 2 root 2 by pi. Input power factor we can calculate as the product of continuous, which is current distortion factor, and the displacement factor. So that will give you 0.9 cos alpha. Active power and reactive power we can calculate using the formula where we have Vi cos alpha and Vi sin alpha. Now this is the comprehensive performance summary comparing the different type of loads, whether it is a R load, RL load in the continuous mode, and the RLE load. We can have the parameter like average voltage, conduction angle, power factor, current ripple, total harmonic distortion, and the applications where it is basically used. So we can have the different type of loads, and this different type of loads will have different voltage, current, power factor, and so on and so forth. So what is the design guidelines that we can use? Select the firing angle based on the required output voltage and the power flow direction that we required. Use the freewheeling diode because it will improve the performance, especially in the rectification mode. Consider using the harmonic filters for power quality improvement, and ensure that adequate SCR current and voltage rating we have with safety margins. So this design guidelines we need to follow depending upon the requirement that we have. Converter topology comparison, if we do now, the midpoint center tap transformer we have seen, the bridge configuration also we have seen with the freewheeling diode also. Now how many transformer we required, what is the PIV rating, number of SCRs, maximum power at a particular current 50 ampere, inverter mode is possible or not, what is the current ripple. So these comparisons we can do. So we can see the number of SCRs, for example, in bridge rectifier is double of the center tap, and one diode extra will increase when we have the freewheeling diode. In PIV rating, peak inverse voltage rating, again the center tap will be twice the bridge configurations, and if we see the current ripple, which is low if we have the freewheeling diode. So depending upon the condition at what we have, depending upon that, these all will changes. So again, let us see the selection criteria. So if we compare the cost versus performance, then the bridge will offer better utilization. If we see the power rating, higher power application will favor the bridge topology. So always we'll go with the bridge topology when we have power rating high. Ripple, if we see, then the freewheeling diode will obviously reduce the ripple, and bidirectional power if we required, then the full bridge, especially in the inversion mode, we need to use. So let us conclude what we have discussed now. So single phase controlled bridge rectifier will offer versatile AC to DC conversion. Firing angle control will enable the output voltage regulation and the power flow control. Load characteristics significantly influence the converter performance. 4-quadrant operation capability make them ideal for the motor drive application. And there is a trade-off exists between the control flexibility and the power quality. If we talk about the performance inside, bridge topology will offer better transformer utilization than the center tap configuration. Freewheeling diode will improve the current continuity but prevent the inverter operation. RLE load analysis is crucial for DC motor drive application. Harmonic content will increase when the firing angle delay is there. So this complete our discussion on full wave rectifier with a center tap as well as bridge. In the coming lecture, we are going to see more on the controlled aspect of the rectifier, that is semi-controlled and full control. Let us discuss that in the coming lecture. Thank you for now.